Hello everyone, I'm Ruan Qingyu, the head of the CMT Sub-1G product line at Hoperf. I'm really happy to be here today to give this online training session. Today's training is divided into 4 main topics. Topic 1, Sub-G has product portfolio. Topic 2, Sub-G has market overview and key technical advantages. Topic 3, typical Sub-G has applications. Topic 4, development and demo. Alright, let's kick things off with topic 1, Sub-G has product portfolio. This slide shows our Sub-G product matrix. We categorize our products along 2 dimensions. The first dimension is modulation mode. We have OOK modulation, which is aimed at cost-sensitive, low-cost applications. And then we have FSK modulation. Chips that support FSK typically also support OOK, which is targeted at mid to high-end applications where better performance and cost-effectiveness are key. The second dimension is based on the chip's main functional attributes. Here we have 5 categories: transmitter-only TX, receiver-only RX, transceiver TX, transmitter with encoding, transmitter with MCU, and transceiver with MCU. For example, the CMT2110A is an OOK modulation transmitter-only chip. The CMT2210LB is an OOK modulation receiver-only chip. The CMT2300A is an FSK modulation transceiver chip. The CMT2189D is an FSK modulation transmitter with an MCU. And the CMT2390F64 is an FSK modulation transceiver with an MCU. Now, let me explain our chip naming convention. All our chips start with CMT, which stands for CMOS Tech Products. The first digit after CMT indicates the product line. For example, 1 MCU or SoC product line. 2 wireless connectivity product line, the one we are focusing on today. 3 sensor product line. 6 power management product line. 8 isolator product line. The second digit indicates the main function, taking the wireless connectivity line as an example. 1 transmitter only. 2 receiver only. 3 transceiver TX RX. The third digit indicates the secondary function, again using the wireless line as an example. 1 basic function. 5 supports encoder decoder. 8 embedded MCU. The fourth digit indicates additional features. Generally, a higher number means more advanced features within that subcategory. A 0 typically means it's the basic model in that subcategory. After these 4 digits, you'll see 1 or 2 letters indicating the chip version. For example, A is usually the base version, B is an upgraded version, and you might see combinations like LB or LH. That covers the basic part name. Next, we have the suffix, which gives information about the operating temperature grade, the package type, and the packaging format. The first letter in the suffix indicates the temperature grade. E means the operating temperature range is -40 degrees Celsius to +85 degrees Celsius, which is what most of our chips use. So, most of our suffixes start with E. The second letter indicates the package type. For example, S usually stands for SOT or SOP packages, while Q stands for QFN. The third and final letter indicates the packaging format. For example, R means tape and reel, and B means tube. Let's look at some examples. CMT2110A ESR, low cost 240 to 480 MHz OOK transmitter. Version A minus 40 degrees Celsius to plus 85 degrees Celsius SOT23-6 package tape and reel. CMT2119 AESR. Low cost 240 to 480 MHz OOK FSK transmitter. Version A minus 40 degrees Celsius to plus 85 degrees Celsius SOT23-6 package tape and reel. CMT2210 LB-ESR. Low cost 300 to 480 MHz OOK receiver. Version LB minus 40 degrees Celsius to plus 85 degrees Celsius SOP8 package tape and reel. CMT230 AEQR. Ultra low power Sub-1G transceiver version A minus 40 degrees Celsius to plus 85 degrees Celsius QFN16 package tape and reel. CMT2310 AEQR. High performance Sub-1G transceiver version A minus 40 degrees Celsius to plus 85 degrees Celsius QFN24 package tape and reel. CMT2157 BESR. Sub-1G OOK transmitter with encoder version B minus 40 degrees Celsius to plus 85 degrees Celsius SOP14 package tape and reel. CMT2189DEQR. Sub-1G OOK FSK transmitter SOC version D minus 40 degrees Celsius to plus 85 degrees Celsius QFN20 package tape and reel. CMT2390F64EQR. Ultra low power Sub-1G wireless transceiver SOC with embedded Cortex M0 core. 64 KB flash minus 40 degrees Celsius to plus 85 degrees Celsius QFN48 package tape and reel. CMT2391F128EQR. Ultra low power Sub-1G wireless transceiver SOC with embedded Cortex M4F core. 128 KB flash minus 40 degrees Celsius to plus 85 degrees Celsius QFN68 package tape and reel. As I mentioned earlier, from a functional perspective, we can group our chips into 6 main categories. Category 1. Transmitter-only TX, mainly the CMT211XA and CMT211XB series. Examples: CMT211A and CMT211A are both in the CMT211XA series of transmitters. Category 2. Receiver-only RX, mainly the CMT221XA, CMT221XB, and CMT221XLX series. Examples: CMT2210LB, CMT2210LC, CMT2210LH, CMT2219A, CMT2219B, etc. We have many more receiver models than transmitter models. Category 3. Transmitter with embedded encoder, mainly the CMT215DEX series. Examples: CMT2150A, CMT2150L, CMT2157A, CMT2157B, etc. Category 4. Transmitter with embedded controller, mainly the CMT218X and CMT216X series. Examples: CMT2189D, CMT2168A, etc. Category 5. Transceiver, currently 2 main models, CMT2300A and CMT2310A. Category 6. Transceiver with embedded controller, mainly the CMT238XFXX and CMT239XFXX series. Examples: CMT2380F64, CMT2390F64, CMT2391F128, etc. For the global market, our main push is on the high-value CMT230A and CMT2310A transceivers, as well as the high-performance transceiver SoCs in the CMT239XFXXX series, like the CMT239-2F512. Let's break them down. The CMT2300AEQR transceiver supports GFSK and OOK modulation with a frequency range of 127 to 1020 MHz. In terms of link budget, it can output up to 20 dBm, and its receive sensitivity is down to minus 120 dBm. It comes in a small QFN16 package, 3 mm by 3 mm, and uses a non-standard 3-wire SPI interface. The CMT2310AEQR transceiver also supports GFSK and OOK modulation, with a frequency range from 113 MHz down to 960 MHz. It also has a max output power of 20 dBm, but its receive sensitivity is even better at minus 122 dBm. It's in a QFN24 package, 4 mm by 4 mm, and uses a standard 4-wire SPI interface. Then there's the CMT2392F512EQR transceiver SoC. Its RF core has the same performance and specs as the CMT2310A. It comes in a QFN68 package, 7 mm by 7 mm, with a Cortex M4F MCU core, 512 KB of flash, and provides up to 36 GPIOs. A quick note on the SPI interfaces. The CMT2300A uses a non-standard 3-wire SPI. The 3 wires are CSB chip select, SCL serial clock, and SDA bidirectional serial data. But note, when accessing the chip's FIFO, there's a separate chip select signal called FCSB. The CMT2310A, on the other hand, uses a standard 4-wire SPI, CSB chip select, SCLK, serial clock, SDI, serial data in, and SDO, serial data out. For both registers and the FIFO, you use the same CSB pin. Now, let's dive a little deeper into our key offering, the CMT2300A, which is all about grid value. It operates on a supply voltage of 1.8 to 3.6 volts and covers a frequency range from 127 MHz to 1020 MHz. It supports OOK and GFSK modulation with data rates from 0.5 kilobits per second up to 300 kilobits per second in FSK mode. Its sensitivity reaches minus 121 dBm at 2 kilobits per second with a 10 kHz deviation on 433.92 MHz. In terms of selectivity, it has an adjacent channel rejection of 30 dB and a blocking figure of 70 dB at 1 MHz offset. That's not top tier, but it's perfectly adequate for its cost-effective positioning. When transmitting at 13 dBm, it typically draws 23 mA. At the max 20 dBm, that goes up to 72 mA. Receive current is about 8.5 mA, and sleep current is just 300 nanoampere, which is 0.3 microampere. This is aimed at applications like wireless metering, smart homes, industrial remote controls, security systems, and wireless sensor networks. For applications where you need higher performance, we recommend the CMT2310A. Think of it as the upgraded, higher performance version of the CMT2300A. It also runs on 1.8 to 3.6 volts, with a frequency range from 113 MHz to 960 MHz. In addition to OOK and GFSK, it also supports 4G FSK modulation. Its sensitivity is excellent, especially in low-speed, narrow-band applications. For example, at 500 bps with a 250 kHz, deviation, it can achieve minus 126 dBm. Its selectivity is also a key strength with adjacent channel rejection up to 60 dB and blocking at 1 MHz offset as high as 77 dB. That's really impressive. Transmit current at 13 dBm is typically 30 mA, and at 20 dBm is about 82 mA. Receive current is 9.6 mA, and sleep current is just 400 nanoampere, 0.4 microampere. It targets the same applications as the CMT2300, a wireless metering smart home, industrial remote controls, security systems, sensor networks, but it also expands into wireless, low-power, wide-area network and Wi-Fi, and is compliant with IEEE 802.115.4G. And that wraps up our first topic. Now, let's move on to topic 2, where I'll give you a quick overview of the Sub-G market and its key technical advantages. The Sub-G module market was valued at 1.1 billion US in 2023, and it's projected to grow to $2.8 billion by 2030. That's a compound annual growth rate of about 10%. Our positioning at Hoperf is to stay right alongside the top-tier international players like Texas Instruments, Silicon Labs, Semtech, NXP, Microchip, Analog Devices, and Maxim. Here in China, we are currently in the leading tier. We sell around 300 million CMT series wireless chips annually. Among those for FSK modulation, our mid to high-end applications, we sell about 75 million units per year. The advantages of our Sub-G solutions at Hoperf can be summed up in 4 key areas. Here are the advantages of the Sub-G solutions we offer at Hoperf, which can be summed up in the following 4 areas. First, we provide highly cost-effective solutions compared with other major RF suppliers. Hoperf not only offers RF chips with excellent cost-effectiveness, but also provides RF modules that integrate matching components. This allows users to reduce costs while also enabling fast development. Second, we offer a very wide selection of product types, covering mainstream frequency bands such as 433 MHz, 470 MHz, 868 MHz, 915 MHz, etc., with modulation options including LoRa, FSK, OOK, and more. Third, we deliver excellent compatibility support. Hoperf provides chips that support the physical layer for various communication protocols. Fourth, with all these advantages working together, we enable users to achieve a fast time to market. Alright, let's move on to our third topic for today, a look at some typical applications. Hoperf's Sub-G products are used in a really wide range of applications. In smart homes, you'll find them in appliance remote controls, remote switches, lighting systems, security systems, and smoke detectors. In industrial automation, they are used for data collection in applications like electricity meters, gas meters, water meters, and thermostats. In automotive electronics, they show up in tire pressure monitoring systems and RKE/PKE keyless entry systems. And in wearables and health-focused consumer electronics, you see them in things like weather stations. Now, let's take a closer look at some of the key application scenarios. This diagram here shows a smart metering data collection scenario. Things like water meters, gas meters, electricity meters, and thermostats in people's homes use Sub-G wireless technology to send their data up to a cloud service platform. Then, the relevant utility companies can process that data. This is a classic example of a low-power wide area network That means low power wide area network. The reason Sub-G is used here is that it's a mature, stable, and reliable technology. Standards like WM-Bus and YSUN are built on Sub-G for this space. Hoperf recommends the CMT2310A, our high-performance Sub-G transceiver, which can handle the requirements of all kinds of complex, low-power wide area network scenarios. This slide shows a fire alarm system based on smoke detection. Smoke detectors use Sub-G technology, making them independent, easy to deploy, and wire-free. When smoke is detected, they trigger an alarm via Sub-G, and nearby detectors can also sound their alarms simultaneously, giving people the fastest possible warning to get to safety. This type of application demands a lot from a standalone wireless smoke detector. It needs extremely long battery life, the ability to listen for alarm signals from neighboring devices for coordinated alerts, and two-way communication for networking and coordinated response. For these needs, Hoperf recommends the CMT2300A and the CMT2310A. The CMT230A is a great fit for users focused on cost effectiveness, while the CMT2310A is better suited for those who need higher performance and the ability to support larger networks. We just talked about smoke detection for fire alarms. Now, this slide shows a home security alarm system. This type of system involves several different types of sensors: an emergency call button, magnetic sensors for doors or windows, passive infrared sensors for motion detection, and a siren for the alarm. These devices all need to be wire-free, easy to install, and have a long battery life. They use Sub-G wireless technology to create a network that can coordinate alerts. For this application, Hoperf again recommends the CMT2300A or the CMT2310A. This next slide shows a weather station system, which is great for gardening enthusiasts. At the heart of this setup shown in the middle is an outdoor weather sensor unit. It integrates sensors for barometric pressure, rainfall, ambient temperature and humidity, wind direction, wind speed, and other weather variables. It uses Sub-G wireless to send this data to an indoor receiver unit, which then routes it to a cloud platform via a gateway. Users can then see real-time data on their phones and even remotely control their garden's irrigation system. Again, for manufacturers focused on cost effectiveness, we recommend the CMT2300A. For those targeting higher performance and a more premium product positioning, the CMT2310A is the better choice. We've just covered topic 3 on typical Sub-G applications. Now, let's move on to topic 4, development and demo. Okay, let's start by looking at the hardware for our demonstration kit. As you can see on this slide, the demo hardware has two main parts: the RF modules on the left side. At the top is the CMT2310A evaluation module, CMT2310AEM, and at the bottom is the CMT230A evaluation module, CMT230AEM. On the right side is the motherboard or evaluation board. When the motherboard leaves the factory, we preload it with demo firmware. Using this firmware, you can quickly test and evaluate the RF performance of the CMT2310A or CMT2300A. When you get this demo kit, you just plug either the CMT2310AEM or CMT2300AEM into the corresponding 10-pin header on the motherboard, power it up, and you're ready to go. The motherboard itself can also be used as a development board. Its main microcontroller is the HC32L136 from XHSC, and we've broken out all its GPIOs to the sides of the board, so you can extend it easily. For the user interface, the motherboard provides 3 LEDs, a 128 by 64 dot matrix LCD screen, a buzzer, and a UART to USB converter. One important note, due to the hardware design, this demo kit with its factory firmware is only compatible with the DirectT versions of the CMT2310AEM and CMT2300AEM modules. It is not compatible with the versions that have electronic switches. For more details, please refer to application note AN241. When you plug an EM, either the CMT2310AEM or CMT2300AEM, into the motherboard and power it up, the normal startup screen should look like the top image here. You clearly see SMOSTech on the screen, and the firmware version will be displayed at the bottom. If the EM isn't properly inserted, or if there's an issue with the hardware, you'll see a screen like the one at the bottom, indicating either no CMT2310A found or no RF chip found. After the normal startup screen, you see the main menu screen as shown here. In this example, we are using the CMT2310A, so the first line says CMT2310AEB GUI. The menu options are displayed in the center of the screen. At the bottom, you see 5 icons corresponding to the 5 buttons K1 through K5. Here's what each button does. K1. Confirm and enter the selected operating mode using the currently configured parameters. K2. Go back to the previous menu level. K3. Scroll down through the menu items. K4. Scroll up through the menu items. K5. Confirm the selected option and return. Now, let's go through the various settings in the menu. Modulation mode. Select OOK, 2FSK, or 4FSK. Operating mode. Choose from modes like Continuous Wave TX, Direct RX, or Packet TX RX modes. Frequency band. Select the starting frequency for your band, e.g. 403 MHz or 863 MHz. Data rate deviation. Choose a combination like 10 kbps 5 kHz. The combinations provided in the menu are essentially the same as those in the datasheet, making it easy to compare test results. Transmit power. Select the output power level of the chip. Preamble length. Set the preamble length for transmitted packets, e.g. 8, 16, 32, or 64 bytes. Note, this only applies when transmitting. Payload length. Set the payload length for packets, e.g. 8, 16, 32, or 64 bytes. Packet encoding. Choose from options like NRZ, Whitening, Manchester, RSC, FEC, or NRNS FEC. CRC selection. Choose the hardware CRC polynomial for the packet, e.g. CCI-TT CRC16 or IBM CRC16. CRC initial value. Set the initial value for the hardware CRC calculation. CRC inversion. Choose whether to bitwise invert the CRC result. Channel spacing. Select the channel spacing in kHz. Channel number. Select a channel number. For example, if you pick channel 10 and your channel spacing is 500 kHz, the actual frequency will be the starting frequency from setting 3 plus 5 MHz. 500 kHz by 10 is equal to 5 MHz. Gaussian filter. Choose whether to enable the Gaussian filter for transmission. Enabling it turns 2FSK into 2GFSK and 4FSK into 4GFSK. Packet count. Set the number of test packets to transmit. e.g. 100, 200. The test will stop and exit automatically after sending that many payload content. Choose what fills the payload, like an incrementing sequence or random numbers. Auto frequency correction, AFC, enable or disable this function. Disable demodulated data output. Choose whether to use this or not. Note, if you are in direct RX mode and need the demodulated data stream for sensitivity testing, you must not disable this output. Packet interval. Insert extra waiting time between transmitted packets to lower the transmission rate. The unit is 10 milliseconds. For example, a setting of 10 adds a 100 millisecond gap between packets. Crystal load capacitance. Select the load capacitance for the crystal oscillator on the chip, ranging from 0 to 31. Note, this setting only applies to the CMT2310A. The CMT2300A does not have this. After you've set up your parameters, pressing K1 takes you into the selected operating mode. Here's an example showing the TX and RX mode bidirectional packet mode. In the center of the screen, you can see that the starting frequency is set to 865 MHz. The modulation is 2 FSK. TR indicates it's in bidirectional packet mode. 000 means channel 10 is selected, and the data rate is set to 20 kbps per s with a 10 kHz deviation. Because TX and RX mode has two sub-modes, the bottom of the screen shows options for master and slave. TX corresponds to K1. Pressing K1 puts you in master mode, active transmitter. RX corresponds to K2. Pressing K2 puts you in slave mode, passive receiver. K3 is for going back to the previous menu. Now let's go through the different operating modes and what they are used for. CWTX, continuous wave transmit. This is a single carrier transmission mode. It's used to evaluate output power, spectral quality, transmit noise, and spurious emissions. In this mode, the data rate setting doesn't matter. Direct RX, direct receive. This mode outputs the demodulated data stream directly. It's mainly used for sensitivity testing, like doing a PN9-bit error rate BER test with a signal generator. Important. In this mode for the CMT2310A, GPIO2 outputs the synchronous clock for the data stream, and GPIO3 outputs the data stream itself. For the CMT2300A, GPIO3 is the data stream output. Also, you must disable the .disable setting, otherwise no signal will appear on these pins. Only TX mode. This is a packet transmit only mode. You use it with another demo board set to only RX mode for a simple one-way transmission test. It's commonly used for outdoor range testing. Only RX mode. This is the packet receive only mode. It's the counterpart to only TX mode and is used together with it. TX and RX mode. This is the bidirectional packet communication mode. As mentioned earlier, it has two sub-modes: master, active transmitter, and slave, passive receiver. In master mode, the device periodically sends a packet and then immediately switches to receive mode to wait for a response packet from the slave device. In slave mode, the device stays in receive mode most of the time. When it gets a valid packet from the master, it switches to transmit mode and sends that same packet back. This back and forth or ping-pong communication tests the performance of the bidirectional link. Sleep. This mode puts the chip into low-power sleep mode. You can use it to measure the current consumption in sleep state. This slide just shows the menu interface for the 6 operating modes we just discussed. CWTX, Continuous Wave Transmit Test Mode, Direct RX, Direct Receive Test Mode, Sleep Mode, Only TX Mode, Packet Transmit Only Test Mode, Only RX Mode, Packet Receive Only Test Mode, TX and RX Mode, Packet Transmit Receive Test Mode. Let's go through each mode in a bit more detail. First, let's talk about CWTX and Direct RX. In CWTX mode, you just need to set the frequency and output power. The data rate, deviation settings don't matter here. To set the frequency, you use the starting frequency, channel spacing, and channel number settings. Together, this lets you hit most target frequencies. You also select the desired output power. Once configured, you start the transmission. This mode lets you evaluate whether the output power meets the spec, check spurious emissions, and measure the transmit current at that power level. While CWTX mode is for evaluating transmitter performance, Direct RX mode is for evaluating receiver performance, particularly sensitivity. So, before entering Direct RX mode, you need to set the target frequency and also select the appropriate data rate, deviation combination, as different combinations have different sensitivity specifications. This mode is most commonly used with a signal generator to run BER tests and to measure adjacent channel rejection and blocking. Once in this mode, the screen shows the selected data rate deviation combination. During testing, you can also see the current RSSI reading. That means you can also use this mode as a simple tool to measure ambient noise levels during outdoor range tests. Now let's talk about only TX mode, packet transmit only. In this mode, besides setting the frequency and output power, like in CWTX mode, you also need to configure the data rate deviation, packet count, and packet format settings. This includes preamble length, payload length, encoding, CRC selection, CRC initial value, CRC inversion, payload content, and packet interval. Once you are in this mode, the lower left corner of the screen shows the number of packets transmitted so far. By comparing this count with the number of packets received by a device in only RX mode, you can calculate the packet error rate, PER, for a one-way link. This is why this mode is commonly used during outdoor range testing to determine the PER at different distances. To test alongside a device in only TX mode, you need only RX mode, packet receive only. In this mode, the main settings like frequency and packet format need to match exactly those of the transmitting device. This lets you test the one-way link. When receiving packets, the screen updates to show the number of correctly received packets, those that pass CRC, and RSSI of the valid packet that was just received. Keep in mind that this RSSI reading is the signal strength of a correctly received packet, the actual signal level. If you combine this with the ambient noise level you can measure using Direct RX mode, you can calculate the signal-to-noise ratio, SNR, for the one-way link at that specific distance. We've covered one-way link testing using only TX and only RX modes. Now let's talk about testing a bidirectional link. For that, we use TX and RX mode. The configuration options are the same as for only TX and only RX modes, but the difference is the two sub-modes, master active and slave passive. The master device periodically sends a packet. After transmitting, it immediately switches to receive mode to wait for a response from the slave device. If it gets a response, the same packet content, it counts it and then proceeds to the next transmission. If it doesn't get a response within a timeout, it also proceeds to the next transmission. The slave device, in contrast, stays in receive mode most of the time. When it receives a packet that passes CRC, it quickly switches to transmit mode and sends that exact same packet back to the master. This back and forth or ping-pong communication tests the quality of the link in both directions. It's a more demanding test than a one-way link. During testing, the master device shows two counts. The number of packets is sent and the number of responses is received. The slave device shows one count. The number of packets is received, which is also the number is sent back. For a perfect link at a given distance, all three counts should be equal and match the number of packets the master was set to send. If there are differences, it indicates some packet loss, and you can analyze which direction might be experiencing more issues. We've covered the main packet operating modes. Now, let's look at the packet format used in this demo. As you can see, we use a simple fixed-length packet structure. Of course, both the CMT2310A and the CMT2300A support very flexible packet structures, but we chose this simple format for the demo to make it easier to do interoperability tests with other manufacturers' products. The packet consists of four main parts: preamble, sync word, payload, and CRC. Preamble. In 2FSK or OOK mode, the preamble is 0xAA. In 4FSK mode, it's 0xCC. Its length is selectable starting from 8 bytes and doubling up to 1024 bytes. Sync word. Fixed length of 6 bytes in the sequence 0x2D D4 2D D4 2D D4. Payload length is also selectable, starting from 8 bytes and doubling up to 1024 bytes. The content can be either an incrementing sequence or random numbers. You can use either field type with any of the packet modes we discussed. CRC. The demo supports three calculation types: CCITT CRC16, IBM CRC6, and the CRC32 defined by IEEE 802.15.4G. You can also choose the initial CRC value, all ones, all zeros, or 0x1D0F, and whether to invert the final CRC result. Our chips actually offer many more CRC options than what's shown here. Additionally, there's an encoding selection that applies to the payload and CRC fields. The default is NRZ, but you can also choose whitening, Manchester RSC FEC, or NRNSC FEC. Finally, there is a gap between packets. The minimum fixed gap is about 50 milliseconds. You can add extra time using the packet interval setting, with each increment adding 10 milliseconds. Note, this interval is the waiting time between transmissions. It does not affect the timeout period in the master mode of bidirectional testing. The timeout duration depends on the total time needed to transmit and receive a packet. Now, let's talk about how to use this demo kit effectively. As shown in the top left of this slide, the demo provides various data rate deviation combinations for OOK, 2FSK, and 4FSK. These options match the performance reference points given in the datasheets. You can use one RFEB Rev003 board with a CMT2310AEM module as your device under test DOT, and connect it to a spectrum analyzer or a signal generator for testing. For example, connect to a spectrum analyzer to evaluate output power, harmonics, spurious emissions, and occupied bandwidth. Connect to a signal generator to test bit error rate, BER, packet error rate, PER, and receiver selectivity parameters like adjacent channel rejection and blocking. And this setup isn't limited to the CMT2310AEM module. You can also use it with your own custom designed module, as long as you break out the necessary interface pins and connect them to the 10-pin header on the RFEB board. As I mentioned earlier, you can use a pair of demo kits, one set to only TX mode and the other to only RX mode, to do a one-way link test. This lets you measure the packet error rate, PER, at a specific distance, and you can use that PER to determine the reliable communication range. In this test, the transmitting side has two main influencing factors: the antenna and the output power setting. The receiving side is influenced by its antenna, the transmitter's output power, but also the ambient noise level at the test site, the selected data rate deviation combination, which affects sensitivity, and the packet length. Shorter packets generally perform better than longer ones. For bidirectional link testing, as we covered earlier, you can use a pair of demo kits, both set to TX and RX mode. You set one as master and the other as slave. Start the slave first, then start the master, and they'll start their ping-pong packet exchange. The same factors that affect one-way links, antennas, output power, noise, data rates, etc., also affect both directions in this bidirectional test. The main purpose of a bidirectional link test is to evaluate the quality of the communication link in both directions at a specific distance, since in real-world applications, the uplink and downlink performance isn't always identical. Alright, that wraps up the content I wanted to share with you today. Thank you all for joining. Next, we are going to show the actual operation of the demos, so you can get a more intuitive feel for what we just covered. Thanks again, everyone. We have now introduced Hoperf's Sub-G product portfolio, as well as its typical application scenarios. Next, we will move into the demonstration section. In this part, we will show how Hoperf devices, including the CMT2310AW and CMT2310AW, can achieve interoperability with other Sub-G transceiver products. This demonstration will focus on interoperability testing across different vendor platforms, highlighting system compatibility and practical RF communication performance. Interoperability is essential in RF wireless communication to build reliable systems and to enable easier maintenance and deployment. Over the IoT product development process, different RF transceivers, or RF SoCs, may be adopted at different stages. As a result, new platform devices may be introduced during product evolution. Therefore, interoperability between different devices becomes a key concern for both developers and end customers. Hoperf is committed to ensuring interoperability across multiple vendors, enabling seamless migration and system-level integration. In addition, we provide complete development tools and example code to demonstrate how interoperability can be achieved with other devices in practical applications. Next, we will demonstrate how to use the CMT2310A EVB to communicate with devices such as the SI463, S2LP, and SX127X. As shown in this figure, the board on the left is the CMT2310AW development kit, and the board on the right is the SI4463 based evaluation module. In this demonstration, we will show how to configure the CMT2310AW so that it can establish communication between the two platforms. Set modulation to 2FSK. Set work mode to CWTX. Set frequency band to 433,000 kHz. Set data rate to 50 kbps with 25 kHz deviation or any other rate deviation combination you prefer. Set TX output power to plus 10 dBm, the module's maximum output power. Set preamble length to 256 bytes. Set packet length to 256 bytes. Set coding format to NRZ. Set CRC select to CRC 16CCITT. Set CRC seed value to 0x0000. Set CRC result inway to off. Set frag space to 000. Set frag channel to 000. Set Gaussian select to BT05. Set test counter to 100. This means send 100 packets continuously in one go. You can adjust this number based on your test needs. Set payload content to random sequence. Set AFC select to off. Set dot disable to on. Set interval select from 000 to 55. This sets the gap between packet transmissions. Adjust based on your test needs. Set XO cap select to 18. This value may vary for different modules. It's used to fine-tune the transmit center frequency. DC-DC enable can be set to either on or off. Set DC-DC frag between 400 kHz and 1140 kHz, depending on the external inductor used. If DC-DC enable is off, you don't need to set this. Set DC-DC voltage between 1800 mV and 2100 mV, based on your receiver power consumption requirements. If DC-DC enable is off, you don't need to set this. Set RX overtime cell to 0000. This is the receive timeout limit. 00000 means no timeout. The receiver will listen indefinitely. This setting is not needed on the transmitter side. Receiver outdoor range test settings. Set modulation to 2 FSK. Set work mode to CWTX. Set frequency band to 433,000 kHz. Set data rate to 50 kilobit per second with 25 kHz deviation or whatever combination you used on the transmitter. TX output power can be set to plus 20 dBm, but this setting doesn't really matter on the receiver side. Set preamble length to 32 bytes or 64 bytes must match the transmitter. Set the packet length to 256 bytes. Set CRC select to CRC 16CCITT. Set CRC sit select to 0x00000. Set CRC result inway to off. Set frag space to 100 kHz. Set frag channel to 000. Gaussian select can be set to BT05, not critical for the receiver set. Test counter to continuous. The receiver will keep listening continuously. Set payload content to random sequence. interval select can be set to 010 or 000. Not really needed on the receiver side. Set PA mode select to switched current. Set PA-ADJ select to hitch power fine. Use the same settings to set up the CMT2310A receiving end. Here we will speed up the video to complete the setup quickly. As shown in the picture, the development board on the left is for the CMT2310AW, and the one on the right is for the ST Micro S2LP module. We are going to demonstrate how to configure the CMT2310AW so that both platforms can communicate with each other. As shown in the picture, the development board on the left is for the CMT2310AW, and the one on the right is for the SX127X module. We are going to demonstrate how to configure the CMT2310AW so that both platforms can communicate with each other. CMT2310AW BER test. BER test instrument E4432B settings. Select real-time iShoe baseband. Select custom. Set custom to on. Set data to PN9. Set symbol rate to 50 kbps per second. Set modulation type to select 2LVL FSK. Set FSK to 0 Hz. Press the FM key on the front panel and set FM to on. Set FM DEV to 25 kHz and set FM source to X2AC. Press the mode key and set BERT to on. CMT23108WPER test. Test instrument settings for receiving packets. Press the Mode key, select Real-Time IQ baseband, then select Custom. Set Custom to On. Go into Data, select User File, then choose the 32-byte file that you've already saved on the instrument. Go back and set symbol rate to 50 kbps. For modulation type, select Pi4 DQPSK, then choose FSK, then 2LVL FSK, and set FSK deviation to 25 kHz. Press the frequency key and set the frequency to 865.1 MHz. Press the amplitude key and set the output power. Connect the module directly using a shielded cable. Once the module is configured and set to receive mode, it will receive the packets from the instrument, and the module will display the number of received packets, the RSSI, and the signal-to-noise ratio. CMT23108W Communication Range Test. CMT23108 to CMT23108 868 MHz outdoor range test settings. Set up the transmitter according to the test requirements. Set up the receiver according to the test requirements. Turn on the receiver, turn on the transmitter, and verify that communication is working normally. Keep the transmitter fixed in one place. Turn on the receiver first, then turn on the transmitter. Move the receiver to a certain distance away. The packets received should match the packets transmitted with little to no loss.